This class handout has a lot of writing in it, and I apologize for that, but there's sort of no way around it. I wanted to help give a structure to walk through systematically so that we end up with that punchline that really shows us, gives us some sort of intuition for why the irrationals are so much more prevalent than the rational numbers. As long as your students have seen long division, there's nothing in here that they shouldn't be able to do. And it's kind of awesome that just knowing long division will give them that sense that the irrational numbers are so much more plentiful than the rational numbers. As for the mathematics, a lot of your students probably, if they've seen long division, will already know that a third is 0.333333 and goes on forever. And that's great. So some of this stuff may be just too simple for your students to start off with, but it's good to rehash it with them. Some of your students may even have things like a seventh or 3/11ths at their fingertips and realize that they have repeating decimals, and that their decimal expansion for the seventh, for instance, has a whole big chunk that repeats and then repeats and then repeats and so on and so forth. But to see more generally that no matter what the denominator is, we're always going to end up with repeating sections. Well, it comes back to that long division thing. And let's say my denominator was 527. Then every time I do a line in my long division, I have 526 possible remainders for that next line. And so if there's only 526 possible remainders at each new line, then after I've gone 526 possible more decimal expansions, I've got to end up with the same remainder. And as soon as I end up with the same remainder, well, from then on, I'm always going to end up with the same remainder. And so we're going to have to loop. And so seeing that implication is not so bad. The reverse implication, well, we start off with something like 0.31313131331. And most students shouldn't have too much trouble seeing that the dividing by 99 really helps out here. On the other hand, say I have 5.423131313131. Well, that's kind of just made up of 0.31313133131 plus some other bit that's just sort of a finite fraction, namely 5.11 or 511 over 100. So I end up with 5.423131313131 equals 0.313131331 plus 5.11. And these two are both fractions. And so if I add two fractions together, I obviously get another fraction. So then we see, so long as it just keeps repeating a section forever and ever and ever and ever, well, we must be an actual fraction. So we're a rational number. So all of a sudden you can start thinking about all numbers as sort of some sort of decimal expansion. And the rational numbers are really just a special subset of those, namely decimal expansions that start repeating forever. And if you think about it that way, if I thought about just writing out some sequence of numbers and calling that a decimal expansion of something, what are the chances that I'm going to pick that sequence so that it just starts repeating forever and ever and ever and ever after some point? Pretty small, huh? And so now you get some sort of sense as to why fractions really don't make up much of the real line. So this little sidetrack is really just sort of totally awesome, because we get a sense of why the rational numbers make up such a small part of all of the numbers. I think that's pretty awesome.